Good morning, good afternoon everyone, and welcome to episode 6 of this series on how to make a Web 3D infinite runner game. Today we'll work on handling events to make our ship move along the x-axis, and we'll even add some animations using a handmade linear interpolator. Are you ready? Then let's dive in. Last time, we saw how to populate our scene with obstacles and bonuses. We created a new virtual anchor in our scene that moves consistently with the grid animation, infinitely, and we used object pooling to simulate the endless reapparition of new objects. Today, we're going to finally work on our keyboard event handlers and have the keyboard arrows fly the ship left and right. Okay, so we want to move the ship along the x-axis depending on the keyboard keys that are currently pressed or not pressed. So, for example, if I press the left arrow key, I want to glide towards the left, and if I press the right arrow key, I want to fly to the right. If I release all keys, I just want to go straight, like in my initial idle state. To begin with, let's do a very naive implementation of this logic and just see what it does. I'll just go to my constructor and add another speed variable, the this.speedx. So that's initially set to 0, and this variable will take one of three values, either -1 if I'm moving to the left, 0 if I'm moving straight, or 1 if I'm moving right. For my key press event, I just need to go to my key down event handler, the one that we defined a while ago, and add a little check to see which key was pressed. So if I pressed the left arrow key, my new speed along the x-axis will be -1, else it will be +1. In the end, I can assign this new value as my current speed x. Similarly, in the key up handler, I just have to reset the this.speedx to 0. Okay, now that I have a speed, I can use it to compute my current translation along the x-axis. And basically, I want to say that I have another variable, the this.translatex variable, that's initially 0. And in my update loop, my current speed along the x-axis increments or decrements this value. This is the basic Newtonian physics concept of speed being the derivative of the position. So the speed is the rate of change of the position, and you simply need to add your current speed to your current position each render frame to apply this velocity to your object. But because my speed is -1 or +1, and so it acts more like a direction than an actual speed value, I need to multiply the this.speedx by a factor to avoid my ship moving too fast. If I save this, you'll see that nothing actually happens. And that's because we're not really applying this X translation to anything. Remember how for the forward movement along the Z-axis we used the shader on our grid to animate the shader and simulate movement? Well, now we need to do the same for the X-axis as well. So to fix this, let's go back to our create grid method and improve our grid object and its shader a little bit. So first we have to create another set of buffer attributes for the vertices that are movable along the x-axis. So this second array, movable x, will be filled with the vertical edges of our mesh. And now we can also pass a new property to our shader, the this.translatex value, and use it in our vertex shader to move the vertical lines across the x-axis. So the code is very similar to the other if statements, except that we check for the movable x buffer attribute, we use the translate x property, and we are computing the wrapped x position. So the only thing that's left to do is to actually update this value in our shader as our speed x and translate x variables are updated. So once again, we'll do this in the update grid method. And similarly to our code for the Z direction, we simply update the translate x property of our grid shader and the x position of the object's parent anchor. And if we save this, we can now glide left and right, and the entire scene moves consistently. So we've successfully implemented a basic event handling logic that lets us control the ship along the x-axis. That's really cool. To make it a bit more pleasing to the eye though, we can make a basic animation of the ship, slightly rolling on its side whenever it changes direction. This will give a better feedback to the player that the action was indeed recorded and that the ship is steering. So what I've done for hyperspeed is basically the following. If the ship is going straight and we press the left or right arrow key, then it starts gradually rotating from its current null rotation to a slight angle around the z-axis. Then, as long as you keep the same key pressed, if the ship has reached its maximum rotation, it stays a bit on the side, but it doesn't continue rotating, so it's stuck at a maximal angle. Then, if you release the key, the ship goes back to its straight null rotation. And if you press the other key, then the ship gradually rotates to match the other z-axis angle. In my original code, I actually used twin.js to compute this gradual lerping between the two rotations. But when revisiting this topic, I realized that we can do it by hand and discover how to create a very basic lerping modules ourselves. So I decided that I would rather show you that. If you want to check the twin.js library though, here's the link. It's really cool for whenever you want to lerp between two values. So they call it twin because they compute the in-between values. And so you can make lots of really cool animations, not just for 3D with 3.js, you can actually use it for lots of things, or even just your data. So yeah, make sure to have a quick look at it if you're interested in these sort of things. For our own lerping module, we go through this in two parts. So first we create a new lerp class that does a generic lerping between two values. And then we'll see how to apply it to our specific use case, so the rotation of our ship. To begin with, let's create a new JS file that's called lerp.js and import it in our index.html file. Now, inside of this file, we'll create a brand new class, so that's lerp. The basic idea is that our lerp objects will be instances of this class. They will each have given, from, and to points that correspond to the initial and target values that we want the lerp object to reach. And they will also have an associated delay. Then we'll have an internal ticker, so a clock, that will be regularly updated in our game update loop to make this lerp object move forward in its interpolation. So this class, just like our main game class, will have two main entry points, the constructor and the update method. But this update method will also take in the time delta between the current call and the previous call to be able to update the internal clock of the lerp object. In the constructor, we'll get our from, to, and delay parameters. We'll also initialize the internal time variable, and we'll set the current value to be the from value. And then in the update method, we want to do a linear interpolation between the 2 points, so the from and to points. A linear interpolation can be written pretty easily in parametric form, meaning that you first define a t-value that goes from 0 to 1, and then you describe your interpolated value based on this t-value. So in our case, the t-value is the ratio of the current time over the total delay of the lerping. This will be 0 at the beginning, 1 at the end of the move, and various floating point values in the 0-1 range all throughout the animation. Then a linear interpolation is simply written as this dot value, so that's the current value that we're updating, equals this from, so that's the initial value, times 1 minus t, plus this 2, so that's the target value, times t. If you're not too familiar with math interpolations, you can think of this as pouring water from one glass to another. So at the very beginning, all of your water is in the first glass, t equals 0, so 1 minus t equals 1, and 100% of the water is on the from glass side. Then as time goes by, the T value starts to increase, and so it's like you start pouring water to the second glass, the 2 glass. And notice how the total quantity of the water stays exactly the same all throughout the process. So you don't add or remove any, it's just about moving it from one glass to another. And at any point in the process, you can say that you have a portion of your water in the first glass and the rest in the second glass. So going back to our math formula, that means that the current value of our variable is a mix of the from and the to values. So that's what the t and y minus t are about. They are the factors, so the proportion of each that you are mixing together. But of course, for this to work next time, so at the next frame, we have to update our internal clock with the time delta variable that is passed from the game update loop, because this will make the t value change next time. And finally, if we've gone over our delay, we'll just delete the object to stop the process. But we have to be careful because for now, our interpolation has a fixed speed. It's as if all delays were always 1 second long. So this means that, for example, if we create a lerp object with a delay of half a second, for now it will only lerp half the way before reaching the end condition. So to avoid this, we have to compute a lerp speed that is just 1 over this.delay and multiply our time delta by this value in the update method. This will basically readjust the speed of the lerped object so that it really goes from the from point to the to point in the given delay. And the final thing that we want to do is add some specific callbacks to execute at critical points of the process. Here, more specifically, we want to do something every time the value updates. Namely, we'll want to update the actual ship rotation. And when the lerp is finished, we'll want to clean up some variables. So to make it easy to hook up our callbacks, let's define 2 functions, the onUpdate and onFinish methods. Those will simply assign a callback that is passed as a parameter to the instance, so that in the update method we can actually check for those and call them if they exist at the right time. For the onUpdate, we'll also send back the updated value so that the optional callback function, if it exists, can access this new value directly. And finally, a little trick that we can benefit from is to make most of those functions return the instance itself at the end, because this will enable chaining these methods and create our lerp object in just one sweep go instead of multiple lines. Okay, so time to go back to hyperspeed. So for our project, we want to tween between 2 rotations for a ship. We'll be using our lerp class to create a lerp object that does exactly that, and that changes the ship rotation on update and is regularly updated in our game update loop. Before we actually create a lerp object, let's first prepare a little variable in our game constructor to hold any reference to such an object. We'll call it this.rotationLerp and initialize it to a null value. Now, in our update method, we can actually extract the time delta computation to a local variable. And this way, if we happen to have a valid this.rotationLerp object at that time, so if it's not null, we'll be able to call its update method with our freshly computed time delta variable. Okay, so we're ready to really use this for our ship. So let's create a new util function in our game class that's called rotateShip that takes in a target rotation as well as the delay for the animation. So this method will modify the transform of our ship to get from its current rotation to the target rotation in the given delay. And the function will simply store a new lerp object in our this.rotationLerp variable and initialize it with the given parameters. For the onUpdate method, we'll want to take the updated value of the lerp object and use it for the Z rotation of the ship. For the onFinish method, we'll just clean up our this.rotationLerp variable and reset it to null. We have to be careful though, because at that point our code will error with some null references, and that's once again an issue with using this and getting the right context. So we talked about it a little bit in the second episode of this series. The this variable is context sensitive, so it doesn't always refer to what you think it refers to. And for now, for example, the this variable doesn't refer to our game instance inside of our callback functions. So the this.ship variable, for example, doesn't really exist. And a common way of working around this is to sort of bake the this variable at the beginning of the rotate ship function. So I'll put it in a $this variable, and then I can pass this safe and fixed value to my inner callback functions. And this way the $this does refer to my game instance and the code will run properly. Okay, all that's left to do is call this rotate ship function in our keydown and keyup functions now. First, let's go back to our keydown handler and change a bit the end. Rather than simply assigning the new speed x value, we want to first check if the new speed is different from the current one. And so only if it's different, we will reassign the speed and start a little rotation animation. Our target rotation depends on the side that we're steering to. As usual, those values are some values that I've tested and that I know work for my scene, but you might have to adjust these depending on your game. And remember that our delays are given in seconds, so here I'm using 0.8, so I'm saying that the animation will last 800 milliseconds. We can do the same in the keyup function to reset our rotation to 0. I'll give it a bit shorter of a delay to make it reset quicker. And now if I save this and I press the left and right arrow keys, I see that my ship gradually rotates to the side. So whenever I change direction, it shifts to the other rotation, and if I just let go of my key, it goes back to its idle null rotation. So that's really cool. We now have a flying ship that we can control, we can steer, and we even have some cool animations. Before we end this tutorial, there's a little fix that we should do in the logic that we implemented last time for object pulling. Instead of using the ship.position.x variable, we should actually look at the translate x variable. So this will make sure that the objects do spawn in front of us in the distance. So today we've seen how to extract the key value from a JavaScript event, how to use it to update some inner values, and we've upgraded our shader. And we've even used some basic math with interpolations to create nice animations. Now that we can actually steer the ship, we're ready to add some difficulty to the game. And so in the next episode, we'll see how to handle collisions with the objects on the terrain, both the obstacles and the bonuses. So I hope you enjoyed this tutorial, and I'll see you in the next one.